the desktop up. It then puts it there. I hit send live, and then people can now see
a green
your
screen.
background. No, that's me. No, sorry. That's the virtual camera in OBS keeps breaking. So I can turn that off. There we go. So people can see your PowerPoint deck and
Cool.
you at the side.
Excellent. I'll wave to people.
And they can wave back. And what we'll do is we'll do questions just at the end, because it's probably easier than interrupting you part way through.
I don't mind at all. If you have something that's really relevant for what I'm talking about right at the moment, it's totally cool. It doesn't matter to me.
Yeah, I mean, you're more likely to get me just constantly interrupting and asking you questions and questions from everyone else. So I'll stay quiet. All right, so feel free to kick off whenever you want.
All right, excellent. Well, good afternoon, everybody. Where do I start? When I first saw this Data.Toboggan, I thought, what is a toboggan? Never heard of this thing. And then I saw the logo, and it was a sled going down a hill. And I thought, that's why I've never heard of it. Because, finding a hill here is exercise enough. I'm a Dutchie. Live in Amsterdam these days, but right now I'm in the middle of nowhere in the north of the country, actually, looking out to some water and a golf course. And we were just chatting in the room in Slack that we're actually allowed to travel during the day, not in the evening. And we're in a hotel room with a proper dinner table. That's what I'm sitting at, and they're going to deliver the dinner this evening at the front door of the room. They're not supposed to bring it in because room service is not allowed, and bringing it to the room and then leaving it there is technically not room service. So, all right, works for us. What else can I say? I am I worked in IT since 1989, hence the gray hair. But more importantly, also for this topic, I worked with the predecessor of Azure Data Warehouse, Synapse Analytics, as it's called now, and it was called APS at the time, or PDW even, when it was in a rack in your data center. And a lot of things are still the same. Didn't change much, at least not the part that I'm talking about. I've done a project for a couple of years, and it involved sticking a couple of 100 terabytes. The data in total is actually more than a petabyte, but the work I did was on a couple of 100 terabytes of data that went into Azure Data Warehouse. That was most of it in just a few tables. There's tables that are over 100 terabytes per table, and there's tens of billions of rows in there. And I learned some stuff, and I thought let's talk about what that part of Azure actually means. So let's dive in there. Right? I do have a data warehouse running, so if the Wi-Fi holds up, I'm on the hotel Wi-Fi, but the hotel is half empty, so the hotel Wi-Fi should be good. And even though I'm in the middle of nowhere, my phone says I have 5G, so I can switch emergency. We'll see. Let's see. This seems to work. All right. What is it called these days? Azure Data Warehouse changed its name to Synapse Analytics, but this is Synapse Analytics, and then what was it again? Mark,
it's
you know this.
Dedicated SQL.
Dedicated SQL pools, right? Who comes up with that stuff? This is the part where you switch on a bunch of compute and you move the slider if you need more, and you can pause it if you want to, but then also it doesn't work anymore, obviously. But there is nothing that comes on right away if you click on it or something. You have to decide up front what you want to do with it, and that the same goes for the data. And it's quite there's some learnings to how do you put your data in there, and where does it go, and how do you decide what the best way is. So let's dive into that. Originally, you just these things have a cost. You just, I think this slide is even older. It says DW or data warehouse units. They go from 100 to 6,000. I think they go higher these days. And that just gives you a fixed amount of CPU, RAM, and I/O that go with them. And these days, my demo thingy has a 2000 C, I think. That means you have 4 big compute nodes with a whole bunch of CPU and RAM. And I should remember to switch that off right away when I'm done with this session, because I think it's $25 an hour or something. So that's not the cheap version, but it can go way up. This is powerful stuff. All right, a little bit of history on how that works. You have from the beginning, people have said, don't worry, you're just talking to a SQL server. It's just a SQL server behind the covers. That's what you're talking to. And that's actually not true. You're talking to a control node, and that control node mimics a SQL server. It behaves like a SQL server. It talks to you through Management Studio, but it's not a SQL server. It just speaks the same language, and it talks to the SQL servers, plural, for you. And it decides how to divide what you asked it to do up to the multiple SQL servers that are underneath. That's basically, in a nutshell, how this works. Now, your data, when you put it in this system, is divided in 60 tables, 60 locations. Always, there's always 60. You cannot choose this. You cannot change it. It has been 60 forever. So that's what you got. You can control how you divide it though, but we'll get to that. Now, you send the query to this control node. The control node decides how to divide up the work and what the different compute nodes should do. The compute nodes are actually SQL servers. They have their storage attached. The storage always 60. Get a command to get some data, give it back to the compute nodes. Where's the animation? Come on, yeah, there we go. Give it back to the compute nodes, and that goes up to the control node, and the control node gives the result back to you as transparently as possible. This is the idea. Now, what does that mean? All right, you can scale this compute. You can say, I just want a little bit of them, or I want a whole bunch. You can make this as expensive as you want. It's not instant though. You have to wait for it a bit, and you lose your connection and a lot of cached data. You have to be. It's actually better to just choose to settle on a certain environment. But I can imagine since the cost can get high, if you have a lot of computing to do at night and not that much during daytime, that you scale it down during the daytime. But this is not something that you would scale up and down every 10 minutes or something. That's not really what you do. But twice a day, that might make sense. Most sites that I've seen, they just pick one setting and they stick with it though. Also, you can pause it. Basically say, listen, I don't want to pay anything. That makes it almost free, depending on how much data you have in there, because it switches off the compute, including the control node, but you're still paying for the storage. So if you have a lot of data in there, it can still be a significant cost if you're not careful. And now, this is how that works in practice, where you have the compute mapped to a certain DW setting, to the cost basically, and it starts at the beginning with a DW 100. If you start one in the portal, by the way, in Azure, it starts with a DW 1000, because that is considered the first production-ready Azure data warehouse, because that is every 500 is a compute node. So 1,000 is 2 compute nodes. That gives you parallel processing. It's a parallel data warehouse in that perspective. So that's the first real one. But for development purposes, you can move the slider all the way back down to a DW 100, which significantly makes the cost lower. And that just basically means you have one compute node running all your 60 distributions of data. And with a 100, I think you're even sharing a computer with others. But you don't have a lot of compute power. But for development purposes, perfect, why not? So when you have it to DW 100, all the storage is connected to your one compute node. 200, it goes up and up. this was the old calculation. These days you have with the C behind it. It used to be called Gen 2, but that just morphed into the general thing. The Gen 1 doesn't exist anymore. But basically, you can move the slider to the right and have your storage connected to different compute nodes. So different SQL servers handle a part of what you've stored there. If you can have a table completely distributed across 60 places and have, for instance, on a DW 2000 that I have, it will have 4 compute nodes, 4 big SQL servers that talk to the 60 underlying tables where your one table is divided upon. So basically each of them does 15 of those tables. Now, when they say it's just SQL Server and you talk to the control node like it's a SQL Server and it just behaves the same way. Imagine for once that imagine that you're doing a select count from a table. In an on-prem system, this is simple. You have one SQL Server and it goes to the one table that it has, and it does a count and it gives you the number. But in this case, it's not one table. You have 60 tables, and in my demo environment where it's a 2000 with 4 compute nodes, 15 of them are connected to each SQL server. So they're not even talking to the same SQL server. So the compute node has to ask 4 SQL servers to each count 15 tables. So that's what they do. They all get a select count from their own tables, 60 of them in total. They bring up the total by doing a sum. That's what happens. So even the simplest query has overhead this way. So a myth that you sometimes hear, or project managers or whatever, everybody goes, if this is really that powerful, can we use this for our OLTP-like systems? Is this not just for data warehousing? And the answer is really simple. No, no, no. No, don't do that. This overhead here should already tell you that every query has overhead, because it has to be split up and do something and then bring the result back. So underneath the covers here, there's a lot of, every SQL server has to make its own maybe temp table, put the result in there, and then bring it back up in a separate temp table on the control node. And then when it's done, it has to do another query on that temp table and bring you the result, and then clean up all these temp tables. That is an overhead for the simplest query. So if you're expecting sub-second response times from your queries, you might not get it. There are some tricks that you can do, but still, you have to be careful there. Now, there are ways to distribute you to tell the system how you want your data distributed. Like I said, you have 60 locations, 60 tables. So if you do a create table, you get 60 of them, but you don't see that. The system arranges this for you. The control node just keeps track of it. It has its own metadata system, and it knows that your table name, what the underlying tables are, and you don't see them. And what you can do is decide how you want your data distributed, because there are some interesting choices to make. For instance, this is the first one. I like it. But there are use cases where this really doesn't work, and it's called round robin. And it's as simple as you take your data and you get a row and you get a row and you get a row, like a deck of cards in a casino when they deal cards. It's just no thought behind it. It's just one after the other from left to right. There you go. So the data just goes, you get one, and then you get one, and then you get one, until all the data is evenly distributed. That's the cool part of this. Because remember, when you have all the data evenly distributed and you give a command to this system, all the compute nodes can do the same amount of work. So you're not waiting for one of them that has to do a lot more than the rest, which would slow the whole system down. That's basically the idea. So when you give this thing a query and everything is round robin distributed, like in the select count scenario, if everything is evenly distributed, perfect. They all have equal amount of work, and it's the fastest way to give that answer. But you have options. You can also say, you know what? I have a key, and I'm going to hash on this key. That way, I know that everything with the same key will end up on the same space, on the same place, and that can be useful. So this one has a key, this one, if I hash it, it goes into bucket number 5. Then there's another record that has key number 2. If I hash that, goes into bucket number 31. Here's a 3, goes into bucket number 46. And here's another 1, and that ends up in bucket number 5 again, because it hashes to the same location. So all the 1s are in the same place. This is useful if you want to join your table with something. If you're not joining with anything, you just want to go through one table with a ton of data and have it do stuff, round robin is a good idea, because all the power of all the compute nodes, it's distributed evenly, so that they all have the same amount of work to do to plow through all that data. But if you want to join 2 tables, and you have to join on the key, and the answer better be correct, and they don't talk to each other. So if your data is not in the same place, so if you have another table that's also round robin distributed, you can't join it, because the join would be incorrect, because the tables wouldn't have that data correctly to join. So what it needs to do, and what it actually does, on the fly, while you're running your query, it's redistributing the data. It's actually moving it for you during a select statement. This sounds like it may slow things down and be a really silly thing, but actually this happens quite fast, and this also makes sure that whatever you throw at it, it will come up with an answer. Not the fastest way every time. So it's better to think about this design up front and just to let it move the data all the time, because moving is obviously slower than having it in the correct place in the beginning. But it's quite powerful. It will come up with a correct answer. It's really fast that way. So if you have 2 tables that you want to join, you could, if you have the same key in both tables, you could hash it on the same key. So everything with the same key that you join on will be in the same bucket, so you can correctly join on it and get the correct data back. That is really useful there. There is one last option. Oh, and one more thing that I have to mention. There is also, be careful with this one. If you have null values, they always go in the first bucket. So if half your table is null, your first distribution, your first table there of the 60 will have all those records. So if you do where blah is not null, then the compute node that services that first table has less work to do than the rest, because it can skip all this data. It will be somewhere else. So a good key to hash on would be the opposite of something like you would think like a date time. It would actually be a bad idea, because you have your data warehouse and all the data for today comes in, and it's maybe 1 billion rows or 100 million rows or just 1 million, and they would all go to the same bucket because they're hashed on today's date. So they might be in the same spot. So the next day, all the data warehouse, all the analytics people will run their queries, and they will all ask for the data of yesterday, because that's all new data. They want to see the new data. And that's all in the same spot. So there's one compute node doing all the work, and the rest is like, yeah, I've got data from 3 years ago. You're not really asking for that, so I'm not going to help you. So be careful there. What you hash it on, you want to make sure that you don't distribute things unevenly, unless you have to do it because the other table is hashed on the same key, and it prevents data movement. That would be fine as well. Now, like I said, these are the 3. No, I only mentioned 2. There's a third one, and I don't have an animation for that. But there is a third one. It's called replicated, and that just basically means a copy of the data everywhere. So imagine you have a huge fact table. You could round robin distribute the fact table, so nice and even spread on a huge table, but then you want to join on a dimension. And if the dimension is not in the right spot, it will move, it will redistribute that data. And if you don't do it correctly, you might even have that actually it will always mostly redistribute the fact table in a different key, so it can join on the key of the dimension, which makes it slow. what you can do is replicate the dimension. That means a complete copy of the dimension will always be everywhere. So you can just join it, and the subquery that it has to do on its own little distribution will be correct because it has a full copy of the dimension. So the join will be correct, and it can bring all the results together. It does a little trick. It doesn't copy the dimension 60 times, but only to the number of times that you have a compute node. So in my case, 4. But this is quite a common scenario. This will work. I can show you later how that works. Here, just to emphasize that if you don't do the distribution correctly, if you hash on something that doesn't make it even, then at some point certain distributions will need more time, and your query is only ready when everybody's ready. So this slows things down. On the other hand, this might be better than having a lot of movement, because moving data might be even more expensive. You need to test this out. So these are the two goals that you have. Minimize the skew, make sure it's all balanced, but also minimize movement. And those two don't work together. It's not like if you fix one of them, then the other one is done as well. You might have to sacrifice the one for the other. It completely depends on your scenario. Now, how do you figure this out? How do you do this design? This is the cool part of Azure Data Warehouse. I had an on-prem SQL server which was 130 terabytes, and every time we wanted to change an index or something, it took 4 days because there was one table that had 60 billion rows or something. And that just, how do you do that? Or let's try a few indexes. I couldn't go to the SAN team and ask for another 100 terabytes of data. That just didn't work. In Synapse Analytics, it does. You just have all this table. You just have all this stuff. So you can just try. That's the cool part. You just go, I have this table here. I wonder what it does if I distribute it differently. I'm just going to make a copy. Even though it's 100 terabytes, it doesn't matter. You can just make a copy. Mind the cost, though. You're still paying for all that stuff, but you don't have to ask anyone, except for maybe the person with the budget. You don't have to connect any storage. You don't have to mine the storage up to a certain, it's not completely true. As long as you're using Columnstore, it's completely unlimited. If your main index is a clustered index, then you have a 60 terabyte per table limit, I think. And we had one where we almost hit that limit, so we had to be a little bit careful, but oh well. It uses compression by default and whatnot, so you can, it goes pretty far. Now, these are the different type of movements. I'm gonna skip over that quickly. There's a whole bunch of them, and they change all the time. But there's it can do broadcast move, means I'm copying the replicated tables to all the other nodes, and there's shuffle move where you go, it was hashed on a key, but it was the wrong key, so I'm gonna reshuffle it. It also moves data while loading. I'm just gonna go across this quick. One thing though, besides querying it and figuring out where it needs to go, a side note is on loading the data is also important in your data warehouse, because even though it does support all the classic methods of putting data in there, like a SQL Server would, you can use bulk copy, SSIS, that just works. But you are talking to the control node, and then the control node has to distribute it to the right compute node. It will hash it for you. The hash algorithm is not public. You do not have access to the compute node, so you can't send the data to the right spot right away. It doesn't work like that. Now, there is an alternative. You can use Polybase, and Polybase figure this out for you. This is basically you telling the system, here's my data in this blob storage, you go grab it. And it will do this from the compute node, so everything in parallel. Now, how does the compute node which data to grab? It doesn't. It just grabs a chunk of the data, hashes it, decides where it needs to go, and sends it to the right compute node, because maybe 75% of the time it got it wrong, right? Still, that is fast, that scales better, and it's faster than the original method. Just a simple side note on be aware on this loading stuff. There's a little slide on which is fastest and slowest. It's actually not true. It just it should have BCP SQL bulk copy and SSIS as slower, and then Polybase as fastest. This is not a sliding scale at all. It's just SSIS, bulk copy, and BCP are the same, and then Polybase is way faster than the rest. Just a thing. All right. Minding the time here. Okay, cool. Row store or column store. This is the thing. If you listen to everybody with, oh yeah, Columnstore is way faster. It's the cool thing. You need to use that. It compresses better. It's faster. Also, there's advantages because it gives you the unlimited storage, and a normal Columnstore, a normal clustered index doesn't. And it caches a lot more because these Columnstore things have read-only blocks or segments, and once you've read them, they stay in a local cache on the compute node on fast mSATA storage. So there's a lot of stuff underneath the covers that are happening if you use Columnstore. So it sort of kind of sounds smart to always use Columnstore, right? But that's unfortunately not true. I've had a few situations where Columnstore really wasn't a good idea, and we reverted back to normal non-clustered indexes and clustered indexes. I'll explain why when I've gone a little bit deeper into the Columnstore thing, because I need to do a thing there first, explain that a bit so I can explain the difference better and why we were not using Columnstore for a certain scenario. Now, should I do that now or should I do it? I'll do this later. Yeah, I'll do this later. I'll switch now to my management studio and show you a few things first on the distribution stuff, since we're there anyway. Let's make this a little bit bigger. What I have, it's almost invisible, but I can zoom back in here. I have my data warehouse here, and it's an AdventureWorks copy, and you probably can't see it, it's too small, but in the icons you can see if it's round robin or hashed or replicated. And I have from the fact internet sales, I'll do a query so I can show you. This is fact internet sales, and I'm joining it with dim customer. And to get the query plan, I can get the query plan here. I can just do it with Management Studio like this. And then you will see that because fact internet sales is hashed on a key, and I'm joining it with dimension, it's not hashed on the same key because the dimension doesn't have the fact internet sales key, so it can't be hashed on the same dimension. Fact internet sales has the dimension key, and it could be hashed on the same one, but what if you join it with another dimension? Then it would be lost again, right? So what it does here is shuffles the data to be able to answer the query correctly. So there's data movement on this query. A better thing to do maybe is if you go, you know what, I'm going to round robin fact internet sales, and I'm going to replicate the dimension, the dim customer, because then fact internet sales is nicely evenly distributed across all the nodes, and dim customer is everywhere. So I can just join them. There's no data movement needed at all. And if I ask for that query plan, you can see it doesn't do any data movement. Now, this is a bit simplistic, maybe even a get and that's it. You can get better query plans if you type explain above it. It will then give you a little XML. Unfortunately, it doesn't understand the XML, so you have to basically copy that and then paste it, and then it's just all in one row. But there's a little trick. If you make an empty file, call it whatever .xml, and open that in Management Studio and paste it there, it understands. Because Management Studio does understand XML, it just doesn't know that I wanted to do it right away. So you can see here, this is quite a query plan. Let's go through a limited number of things. There's a number of distributions is 60. It's always 60. So there's 4 nodes, and there is 15 distributions per node because 60 divided by 4. And you can see at some point that it does the shuffle move here to make sure that the fact internet sales gets shuffled and redistributed on customer key, because I'm joining with dim customer. And once it's done that, I can join it correctly. And then give the data back, and then drop the temp table. So this is this is an extra step here, and there's data movement. Now, if I go to, let's close a few windows to not confuse everybody. If I go to the other one and show you the explain for that, and copy that quickly underneath. You can see it's way simpler. It's replicated. The dimension is already there. The join can be done. The data will be correct. All the data is there for the dimension. I don't have to move anything. Just join it everywhere on all the 60 tables and bring back the result and collect it and give it back. That's basically what it does. Way simpler, which is good, and no data movement, which is also good. That's basically how this distribution stuff works, what you have to think about. Now, another thing, let's go back to the Columnstore under the demo. This is a obviously simplified explanation of how Columnstore works. Let's say you have a normal table with a make, a model, and a color. There's 2 Audis, 2 BMWs, different colors, different types, different models, and it goes and compresses this. First of all, it's called Columnstore, so it's going to take the rows at the columns make, model, and color and stick them into separate data types, data files, data structures. I should say structures, because they're not in one row anymore. And then it's going to take the unique values that are in, for instance, the make column, and goes, I'm going to just number them, and I'm going to make like a dictionary on top of my file. So it's going to say I've got an Audi and a BMW, and they're 1 and 2. And then in my file I have a 1, 1, 2, 2. And I'm doing the same for the model and the color. That's one step. Then it's taking the number of times it has an Audi and compresses that, and just saying, you know what, I have an Audi and I have it twice. And then I have a BMW and I have it twice. And it tries to do that for the rest as well. And what you're noticing here is that it's now losing the connection between the rows underneath, right? It's not like the first row in the second row in the make is the second row in the model. That's not the case anymore. So it has to do more computing to figure out what belongs to what. So here's one tip already. If you're used to doing select star, and people are saying that's not a cool idea because you lose the ability to use non-clustered indexes, it's even worse with Columnstore because it has to recompute all the time which belongs to which. So select star is even slower in Columnstore. Be careful there. Just pick the columns that you need, because it also doesn't have to reconstruct all these columns again and figure out what goes with what. It also can just completely skip the column because they're separate structures. So it just doesn't have to look at them at all, which a normal index cannot do. So that makes not selecting a column way more important on the Columnstore. And lastly, there is also in every file, it keeps a track of a min and a max. So it can take, it does this in segments. So I think it was 1024 times 1024 was the perfect size of one of these segments. And that's 1,000,000 something. You won't get 1,000,000 something because at some point it's going to stop compressing into these structures and go, okay, I've either run out of space in my dictionary on the top because that's 16 megabyte or something. So if you have too many different values, it's just going to stop and move on to the next one. Or maybe you don't have enough memory because compressing large chunks of data takes up memory. So you need a lot of memory. So you might end up with more of these segments than you think. And per segment, it has a min and a max of a bunch of values. For instance, the make has the minimum value is Audi and the max is BMW. So if you're querying for Porsche or whatever, it's going to just skip the whole segment. It's going to read the header, or I think it's the footer in this case. No, that's Databricks. Never mind. And it's going to read the metadata basically of the segment and go, okay, Audi to BMW. There's no Porsches in here. Skip. Next. So it can skip a whole bunch of stuff. The one thing though that's missing is a tree, a B tree. This is not an index in the pure sense of an index. This is just basically an effective table scan that you're getting, right? It knows how to skip a whole bunch of stuff, but there's no tree to point it to the right place right away where it can do a search. Like, okay, Audi's, we're going to go left and then to that place, and then hey, we've got the right spot, so I can do a scan from here. That's not how that works. There are a few tricks that you can use to figure out which column to start with, and you can partition things, but in the end, basically, still a fancy scan that you're getting. So it's really powerful if you have terabytes and terabytes and terabytes of data, and you have unpredictable queries where you can't have an index for everything. You just don't know. They're analyzing this stuff and just throw weird queries at it. This is good. This is fast. It will just do these scans really effectively. Skip all the segments that it doesn't need because it can see the min and the max. Skip all the columns that it doesn't need. Partitioning, it can skip all that and just come back with the data that it needs really fast. And it's really well compressed as well. There's more compression stuff in there. But this is not a Columnstore session. So one situation that I had was I was for a fraud detection department. I can't really say what it was for, but it was a table with tens of billions of rows, like 60, 70 billion rows. And it was, here's a number, magic number, can't say what it was. Here's a number, give me everything from this number for the last 3 months. And the scan would give back 20, 30 seconds to give back the right number. But the on-prem SQL Server had a non-clustered index exactly on the right spot. It would find the 50 to 150 rows right away and then do 50 to 150 key lookups in the clustered index because we needed a select star. We needed all the data, and that was pretty fast, and it gave back the answer in like a second. So people not happy. So this is where we thought, okay, what if we combine the Columnstore index with the non-clustered index, so we can do the lookup in the non-clustered index, and then the search in the non-clustered index, and then do a key lookup in the Columnstore index. Turns out, Columnstore indexes key lookups just don't scale. Can I say out loud that it's rubbish? It really doesn't scale well. If you find 2 or 3 records, it's fine. If you find 10, you can already sense that it's a bit slower. If we had situations where 50 to 150 rows, it would take minutes sometimes. It was ridiculous. So this is where we failed back, basically, not using the Columnstore, and went back to a clustered index to make that work. I think I'm like 5, 6, 7 minutes I have left. So to summarize, make sure you make good choices on how to load this thing. Also, when you load it, you better load big chunks, right? Columnstore is effective if you have maximum 1 million rows, but a minimum should be 100,000 rows. So the dictionary should be okay, but also the amount of memory that you're using should be good. You can make a different connection with Synapse that gives you more memory to do your loading. And you should give it enough rows to handle, right? If you just insert 1,000 rows, nothing much is happening. Now, before you think, I'm just going to insert 1 million rows. No. You have 60 distributions, remember? You're going to have to give it 60 million rows every time to be up to the maximum effective level. So I know that's not going to work for most loads, but think of column stores as you need a lot of data. That would work nicely. So for dimensions, small dimensions, maybe not, right? And in certain scenarios, like I just mentioned, maybe not even for your bigger tables, but that totally depends. It's a really powerful tool, but there are scenarios where it doesn't work. I think that's it. I think I'm there. I've got 6 minutes left on the clock, I think. Mark, any questions? He went out for a coffee. Can't find the unmute.
No major questions, but I was going to ask you about maybe some of the newer stuff that's helped with performance, like the caching, the result set caching, maybe, because although it's kind of come along relatively recently in the life of the product, but I think I found some challenges with it, where it's actually made things worse, because it's all down to workload. But what's your sort of experiences of that?
So we've looked at it, because the result set caching does, it just literally caches a result set for a query. So if you do the exact same query again, it doesn't have to go through the data. It just goes, oh yeah, I have got this result set already. Here it is. We had about 1,000 users on this system, and they were all going, give me the last 3 months for this number. And it was fraud analysis, so I can't really say what the number was, but here's a magic number, and there's a lot of data in this table. Give me the last 3 months. And that would the result set caching would only help if you run the exact same question again with the same number. And they would just all be asking for different numbers. So the result set cache would it just wouldn't work. Sorry, you were going to say something?
Anything with time-based. So if you've got any non-deterministic functions, so get, date, etc., they aren't cached, because when you say give me everything from that table where before a certain date, before get date, and then I run it, that get date is completely different.
They keep changing the system, though, even though if you're not watching, like tomorrow it could be different. There used to be a scenario where if you wanted to generate a date time in a column, they said you should do it outside of the system, because if you do a get date function on an insert, a get date from what? If you have 4 compute nodes, and it's no guarantee that these clocks are all the same. So they would do it in one spot and then copy it across. It would slow the thing down. But I think they've become smarter and smarter and smarter all the time with this. So it might be that a best practice that they used to have is not the case anymore. In the beginning, there were not even automated statistics, right? Autostats that didn't do that. You had to create your own statistics, and now it does.
Well, yes, it creates them when you first query a table, but it doesn't keep them up to date. That's something that is coming, but it's not. Yeah, there's a lot of stuff which isn't there that people expect to be there, and I think they get so used to SQL Server that they see this other product and they go, "Oh, well, it's just SQL Server, but on steroids." No, it's actually it's a bit more different than that.
It is. If in our scenario where we had our on-prem thing of I think it's now 160 terabytes, because it's still there, but we can't maintain it anymore. They are creating we would love to have a separate index. We have it on our wish list, but it's 4 days of downtime to create the index. That's ridiculous. The SAN team is angry with us because we take up a lot of their expensive space. And the loading of the data, the new data, comes in so fast. There's so much that anytime we make a mistake or anytime something blocks, we're behind a day, and that's really not cool. If you're trying to fix fraud cases and you're looking into an active case and it's just 3 days behind, you have to wait until it catches up. And we now have it running in parallel in this data warehouse, and it doesn't run behind anymore. It can keep up easily. It's no problem at all, and we can tinker with it. We can create other. You can't. It's not magic. You still can't do. I've got a 60 billion row table here. Do a select into. Just make a copy. You want to do that in parts because you're gonna run out of memory at some point. But it's so powerful. And the power is not in the fact that it's just more powerful, but in the fact that you can experiment better to find better ways to do things. So With this on-prem thing, it's like playing Tetris, right? In the beginning, it's fine, but at some point, you already see that you're gonna lose. You just can't keep up anymore. And with this thing, we have the complete sense that we have it under control. You can throw other stuff at us now because we can handle it. It's fine. Just move the slider a bit, and it's all good. All good.
I mean, I've worked with a couple of customers that do scale during the day, and one of them scales. They scale down overnight and actually scale up during the day to do some batch processing, which comes in just before sort of 9, and then they keep it high to get lots of queries in and lots of people on it, and then overnight they don't really have a lot of workload. So it's kind of unusual because normally you'd expect to scale up overnight, push that workload through, and then during the day, well, people are just querying it. But it's one of those things where it's very different for different customers, and I find that it's you have to tweak it for them.
That's what I noticed as well. That even per table or set of tables, it depends a bit on how you access this thing. What is your common usage of it? That depends, and that decides how you're going to distribute it. Are you going to use Columnstore or not? And the cool part is that you can make a mistake. That's fine. Just make a mistake. Notice that it's doing a lot of work, and you can just try it by copying a table across. Maybe this will work better. Let's make I know it's 10 terabytes, but let's just make a copy. You can do things like that, and that's what I like about it.
Actually, there was a question. Actually, what are your experiences of the lower level DWUs? So between like 100 and 400.
So they're basically not distributed at all. They're just one system, and I think even the 100 is shared, but I'm not sure. But still, even the single units, the single compute units, that's a lot of CPU and memory and storage power that you're getting. They're not low level systems at all. So
it's 60 gig of RAM for a 100, so per 100 meg. So I think it's 300 gig or something per node. It's on the I pasted in the link to the docs with the sizes. So.
I'm never sure if this is public information or not. So
oh yeah, that is. I think the main difference between the lower ones, the 100 to 400, is the compute and the controller on the same machine.
Right. So we're using in production now a 2000, and we're going to, and that was during the figuring it out scenarios where we made copies of, we literally made copies of 100 terabytes of data here and there without thinking, and just let's see what it does. And we're now ready. We've got a scenario that works. We've done we're past the experimental phase, and we've seen that it doesn't need the compute, and we're going to go back to 1000, and the development happens on a 100. We're just doing that on a 100, so the costs are okay. The 100 is totally cool for development.
Oh, I mean, so the thing that I would recommend if you're trying it out, and I'm not pushing my YouTube channel at all, but what you do is you set it up as a 100 and then set up an ADF job or another job that shuts it down when you're not using it. And then you're not paying that cost when you shut off and you forget to turn it off at night. And then you come back in the morning and then you've got a bill of, even on a 100, which is about £1.50
an hour.
Yeah, which isn't very much. But if you leave it running all weekend, you'll notice it on your, MSDN subscription. It eats into that very, very quickly.
Exactly. Yeah.
I was going to say is the storage cost dropped, I think, at the last conference or something. So it was £127 or something. A terabyte, and it dropped down to the same cost as premium storage, so 20.
Yeah, I do think they made the compute a bit more when they dropped the storage cost. I'm not sure.
Oh, I hadn't noticed that. Oh, that's interesting. Okay. All right. let's see if we've got any more questions. So we could talk all day about I know how interesting it is for everyone else.